All right, does everybody have what they need? Okay. I want you to open your books to figure 5.4, which is on page 115. Okay, so we can see the example of this centripetal force. Okay, the figure that I want you to look at is on page 115, so you can see that that motion is happening. Okay, we talked yesterday that the acceleration vector and the velocity vector should be perpendicular to each other because the velocity vector is drawn tangent to the path. Okay, now you see that that force vector is also perpendicular to the velocity vector. Okay, so if you look at your book on page 115, you can see that that hand is still exerting the force. Okay, it's still pulling that in. I want you to read page 116, the top paragraph, about the centripetal force. Okay, page 116, the first paragraph. Okay, so this practice problem may look a little familiar. I think this is one that we did yesterday, except we're adding to it. Okay, so it's okay if these numbers look familiar. We did that yesterday. We're going to add to it today to find force. All right, so since we're dealing with forces, we're going to have to go back to a free body diagram, okay? And the free body diagrams for these objects are pretty simple, okay? This is an object on a string that's rotating in a horizontal type pattern. So this is an example in your book on page 117. If you want to follow along or if you want to look at the full free body diagram there, you can. But our basic free body diagram looks something like this. We have our object, we have gravity pulling down on it, and we have a force of tension, which is the string attached that's rotating, that's moving it in that circular path. Okay, so that's what our free body diagram looks like. Force of gravity is pulling down on the object, force of tension is what's keeping it upright. Okay, so what can we pull from this problem? What things do we know? Yeah, the radius. Mass is 0.15. What does this part tell us right here? Makes 2 revolutions per second. Frequency. Okay, good. So frequency is 2, which makes our period what? 0.5. Yeah, 1/2. Okay, because remember T equals 1 over F. So T equals 1 over 2, which is 1/2. Okay, or 0.5. So if we want to end up solving for our force here, we want to end up solving for our radial force here. And what equation is that we just found? Yep, mass times acceleration, which also equals v squared over r. Okay, so that's going to be kind of our overall goal. Remember, this FR right here is just like our F net. Okay, that's going to be the same as F net. Okay, so do we have a velocity here? No, we got to solve for velocity first. So our velocity equation that we learned yesterday is v equals, good, 2 pi r over t. So these numbers we do have. 2 pi times radius, which is 0.6, over t, which is 0.5. Should get something around 7.54. Okay, so now we have our velocity, we have our radius, we have our mass. We want to solve here for our net force. Okay. So FR equals mass, which is 0.15, times v squared, 7.54, over r, which is 0.6. What'd you get, Brian? 19.2. Yep. What are our units then if we're solving for force? Yeah, newtons, good. Okay, so that's the amount of force that has to be exerted in order for this object to swing at that speed. All right, any questions? So it says a 0.25 kilogram ball is attached to a string rotating in a horizontal circle of radius 0.5. The ball revolves 2 times every second. What's the tension in the string? Okay, it's 2 times every second. Okay. It's all right. So our free body diagram will look the same. Our force of tension is pulling toward the middle. Gravity is pulling down. Mass equals 0.25, radius equals 0.5. So what's the 2 times every second telling us? Frequency or period? Frequency, yeah, which then we can make into t or period. Okay, so frequency equals 2, which means t equals 0.5. Okay, so we should go in the same order here. Solve for velocity, and then we can solve for our force. Something that we need to remember here is that this force, this tension force that's pulling us to the middle, okay, is going to be the same as our radial force. You can label it either way, okay? So that we're still solving for the same thing. This is still our net force because it's the only force acting in the horizontal direction, and that's what we're paying attention to right now. All right, so our free body diagram here should look something like this. If we're at the very top of our arc, okay, here's our circular path, and we're at the very top of it. We're going to have tension, which is the string pulling down, and we're going to have force of gravity pulling down also. Okay, those are both going to be acting when it's at the top of its path. Okay, since we're looking for a minimum speed, we're looking for the absolute bare minimum tension that we can have in this string in order for it to stay on its path. Okay, so since we're looking for the absolute bare minimum where this string is tight or taut, okay, we're going to use our F-net equation, and we're going to say that force of tension in that case is 0. Okay, because it's just exactly enough for that speed to keep moving it forward on the path. Okay, so if we draw our F-net equation here, F-net equals force of tension plus force of gravity. So why did I add force of gravity rather than subtract it? They're going in the same direction, and we chose the center of the circle to be the positive direction. Okay, we got to choose, when we're dealing with vertical things especially, we deal toward the center of the circle is the positive direction. Okay, so these are both pointing in the positive direction, so we're going to go F of tension, or force of tension plus force of gravity. Okay. However, since we're looking for a minimum speed, we're going to assume, and we're going to say that force of tension equals 0. Okay, because it's just at that second enough to overcome that to continue on its path. Okay, so let's go ahead and start making our list here, picking our variables out. Mass is 0.15. What's the radius? Good, 1.1. So it's at the end of this string. That means that string, as it's rotating, will become the radius of the circle. Okay. So how can we go about solving this? Any ideas? Good. Yep, we're going to do our substitution in this equation. So mass times AR equals mass times gravity. Okay, which will mean we'll substitute mass times V squared over R equals mass times gravity. So do we have the mass? Do we have the radius? We don't have velocity because that's what we're solving for. We're solving for that minimum speed. We know mass and we know gravity. Do we need to plug in negative 9.8 here or positive 9.8? Positive, because it's going toward the center of the circle. Are there any questions as to how we rearrange this equation to get v by itself? Yeah, bro. Yeah? Okay, so we're going to take 15 times 9.8, which gives us 1 point. Okay. Yep. So then we're going to divide by the 0.15. Divide by 0.15 on this side. I'll go ahead and write it out. And then times by 1.1. Yep. Yep. So divide by 0.15, divide by 0.15, which gives us v squared over 1.1 equals, I don't know what that number is. What is it? $10.78? What's 1.47 divided by 9? Yeah. Yep. So then we multiply that times 1.1 and we get 10 point something. And then we square root that. So overall we should get 3.3 meters per second. Yeah, Cole. Would the 1 point class cancel in the beginning? They could. They could. Yeah. He's asking right here. Yeah, they could. Okay. Any questions here? So 3.3 is the exact speed at which that object would have to be moving in order for it to stay on its path.
Okay, so what was the final answer?
3.3?
Yep.
Okay. So now we want to look at the tension in the bottom of the string when it hits the bottom of its path. Okay? We're going to, just for this problem only, assume that the velocity is twice what it was at the top when it gets to the bottom, okay? And it's for this problem only, okay? So our free body diagram at the bottom is going to look a little different. Force of gravity is pulling down, but force of tension this time will be pulling up if it's at the bottom of its arc. Okay, so for this problem only, we're going to assume that the velocity is 2 times what it was at the top of its arc. The mass doesn't change. The radius doesn't change. The velocity will be 2 times 3.3, which is 6.6. So now when we look at our F net or F sub r equation, we're going to take force of tension minus force of gravity. Okay, does everyone see that F sub r and F net should be the same thing? That's our overall centripetal force. Are we clear on that? Yeah. Okay. So we're going to take tension minus gravity. We can substitute right here. Mass times v squared over r equals force of tension, which is what we are solving for, minus mass times gravity. Go ahead and get the numbers plugged in and solve for force of tension. Okay, so as you do this one on your own, make sure that you draw your free body diagram. You pick things out of the equation to make your list with, or pick things out of the problem, I'm sorry, to make your list with, and try and pick an order of equations that you're going to have to go with. Okay, okay, we should have got 4.5. We're learning more.
Really? For real? Wait.
Go ahead and try this one on your own. Okay, so the reason you feel like you're moving outward when you travel around a curve in a car is because your body is trying to stay traveling in a straight line. Okay, because Newton's law says an object in motion will stay in motion until acted on an outside force. Okay, so that your body wants to keep moving in a straight line, yet the car, the friction, the car door maybe, are trying to keep you moving on that circular path. Okay? So objects are acting on you to keep you moving on that circular path. Okay. What is it that keeps a car from sliding off the road when going around a curve?
Friction.
Yeah, friction. Friction. Good. Okay, frictional force is not great enough to keep you on that curved path. You will leave the road, right? You will slide off the road. So why is it that when it's icy, it's harder to stay on the road? Yeah, there's less friction, okay? Friction is reduced because it's slick. So what has to happen in order for you to drive safely around a curve on an icy road? Yes, your speed or your velocity has to be decreased, okay? All right?
Yeah, because of friction. Why does that make sense? Because like your body keeps trying to go forward and your body
All right. Had you ever thought about it in that way, or you just think when the roads are icy, we have to slow down? Did you ever think of it in terms of friction, or no? Yeah. Traction, friction, kind of the same thing. Yeah. Okay. How many of you are really good drivers in the snow? Only Cole? Cole's our only good snow driver? Oh. How many of you are terrible drivers in the snow? Broken.
Thank you.
I drive like 6 miles an hour when it's like snow on the ground at all. I hate driving. Ugh. I hate driving in the snow. Alright, let's try one with friction here. So, when you're driving around a curve, let's think about it this way. When you're driving around a curve, do you want the force, the centripetal force to be greater, or do you want the frictional force to be greater? Frictional force, so that you stay put, okay? So we're going to try this problem, and we're going to examine whether this car can safely make it around the curve at a certain speed, okay? One is going to be with a dry road with a coefficient of static friction of 0.6, and the other one's going to be with an icy road, which has a coefficient of 0.25. All right, so we're going to do the dry road first. We'll see how it works out, and then we'll try the icy road. So let's take a look at what our force or our free body diagram looks like here. Here's our car. Gravity's pulling down on it. This case, since it's on a surface, we have a normal force pushing up on it. We're going to have some frictional force, pulling us in. Okay. Frictional force going on the car as it goes around the curve. Okay. So from our problem, we can pick out the mass, which is 1,000. We can pick out the radius, the velocity, which is 14, and the coefficient, which is 0.6. Okay? So we're going to have to solve for both the frictional force and the centripetal force. You can choose which one we do those first, right? Because we're going to have to compare those two, because we want which one to be larger, we said. We want frictional to be larger. So we're going to have to solve for both of them. You can choose which we do first. Okay, so tell me which one you want to do first. Friction. All right. So we're solving for friction. Frictional force first. So what's the equation for a frictional force? Times the normal force. There we go. So how do we go about solving for the normal force here?
It's the same as the force times gravity.
Yeah, it's the same as a force of gravity, okay? Because the car's not jumping up and down here. It's staying on that surface. So F sub n will equal mass, which is 1,000, times 9.8, which is 9,800. So now we'll go force of friction equals 0.6 times 9,800. And what do we get?
5,800.
Okay. So there's our frictional force. How do we go about solving for our centripetal force? What's our equation for that?
So where is that on the?
This is our net force. Remember, our centripetal force is our net. So we're going to look at only our horizontal, okay, which is our frictional force.
F net equals whatever that minus force of friction.
Nope.
R equals
Oh, yeah. We're going back to our original centripetal force equation, okay? All right, Noah, what'd you get?
3,000.
Good. And units? So there's our centripetal force. Okay. So will the car make it safely around the curve? Yeah, because Yes, because frictional force was greater than the centripetal force, so it will stay on the road. It will be the friction between the tires and the road will be enough to keep it from skidding or sliding. Okay? So now let's try it with the icy road conditions, and we'll change our coefficient of static friction. Okay? So I'm just going to get rid of this part right here. And we're going to change to our icy road conditions, which makes this 0.25. Our normal force stays the same. And what does our, yeah, Cole? 2450 newtons. So what's going to happen here? Yeah, he's going to slide. He's going to be in trouble. So my way of thinking through this problem would be you solve for period first, then velocity, then your centripetal force, which equals your frictional force. Then you can solve for the normal force to find your coefficient. That's kind of my thought process through it. There's multiple ways to get to your end answer.